Free body diagrams are a problem-solving approach that we typically use when dealing with Newton's law problems, dealing with problems that involve forces. With the free body diagram, you depict the object that may or may not be accelerating with a dot, and then show all of the forces emanating from that dot in the directions in which they are exerted. So you can see here we have a couple of examples. First we have some soap hanging on a rope, and the soap we represent with a dot, and then we show the forces that are acting on the soap. Since the soap is hanging near the surface of the earth, its weight will be pulling downward, so the force of gravity is in the downward direction, and then the rope will be exerting an upward tension force. Here we can see a man pulling a sled that's filled with wood, and so here we represent the sled filled with wood with a dot. That's the object in question. And then we show the forces acting on the sled. So in this case, the sled's weight will be pulling downward. The normal force that the ground exerts on the sled is in the upward direction, and then the tension force from the rope goes along in the direction that the rope is attached to the sled. We've been using this approach in problems that we've been looking at already, and we'll continue to use them for future force problems. So here's a strategy you should use whenever you encounter a problem involving forces. First, it's always helpful to sketch a picture of what's going on and show the forces. Then, replace the object with a single point and redraw all of the forces acting on that point. By representing the object as a point, it makes it a lot simpler to split the forces up into their x and y components. Then break the forces into components and sum the forces in each coordinate direction. Then finally, we can apply Newton's second law to each coordinate direction. So we can sum the forces in the x direction and set that equal to the mass times the acceleration in the x direction, and then do the same for the forces in the y direction. So let's take a look at a few different examples where we follow this procedure. So in this first example, we have a very simple problem where we're pulling upward on a suitcase with a force of 115 newtons. The suitcase accelerates upward at the rate that's given, 0.725 meters per second squared, and we want to know what is the mass of the suitcase. So let's take a look at this example problem. As we stated before, the first thing we really want to do is draw a picture showing the situation. So in this case, we have a suitcase. So here is the suitcase, and the suitcase has a handle, and then there is a hand that is pulling the suitcase upward. So the suitcase is accelerating in the upward direction. Next, we want to draw our free body diagram. So we represent the object in question, in this case a suitcase, with a point, and then we draw the forces emanating from that point. So for this suitcase, its weight will be pulling downward. So we have mg in the downward direction, and then we have the upward force being exerted by the hand. So here is the force of the hand, and we happen to know that that force is 115 newtons. Okay, so those are the only two forces that are acting on the suitcase. There's no normal force because in this case the suitcase is being accelerated upward through the air. It's not resting on a surface, and so there's no normal force in this situation. Then next we split the forces up into x and y components. In this case, that's really simple because all of the forces are in the y direction. So the force of the hand has no x component. It's just going upward in the y direction. And the weight likewise has no component in the x direction. It's going downward in the negative y direction. So then we can sum the forces. There are no forces to sum in the x direction, but the sum of the forces in the y direction is equal to the force of the hand minus the weight of the suitcase, and then those forces are going to sum to the mass of the suitcase times its acceleration in the y direction. So then the question that we want to answer is, what is the mass of the suitcase? So we need to solve this algebraic expression for the mass of the suitcase. So that's probably most easily going to be done by taking all of the terms that have mass in them and moving them to one side of the equation. So I'll add mg to both sides, which gives me the force of the hand is equal to mg plus the mass times the acceleration in the y direction. I'm solving for the mass, so I'll factor it out of these two terms. So mass g plus acceleration in the y direction. That's equal to the force exerted by the hand. And then finally, I can divide both sides of the equation by g plus ay, and the mass of the suitcase is going to be the force exerted by the hand divided by g plus ay. So now that I have a expression that I've solved for the thing that I want to find, I can plug numbers in. So the force of the hand is 115 newtons. G, of course, is our familiar 9.8 meters per second squared, plus the acceleration in the y direction we're told is 0.725 meters per second squared. And if I put that into my calculator, I get a number that's about 10.9 kilograms. So this would be the mass of the suitcase. So let's look at another example problem. In this example, we have a 20 kilogram child sitting on a 5 kilogram sled. The sled rests on a essentially frictionless ice and is pulled by a rope that's inclined 20 degrees with respect to the horizontal. The rope pulls with a tension force of 10 newtons. What's the acceleration of the sled? Okay, so like before, the first step is to draw a picture of the situation. So in this case, I have a child sitting on a sled. So here's the child sitting on the sled, and the sled is being pulled by a rope, and the rope is inclined at an angle of 20 degrees above the horizontal. So the next step then would be to draw a free body diagram showing the forces acting on the object. The object in this case is the child plus the sled. So if I draw my free body diagram, it's going to look something like this. So here's the dot representing the child plus the sled. And as always, I have weight pulling downward. Here the mass is the mass of both the child and the sled put together. Since the sled is sitting on the ground, there's going to be a normal force that is perpendicular or normal to the flat ground. So I have normal force going upward. And then of course the third force is the rope. And the rope is inclined 20 degrees from the horizontal. So that would be the tension force coming from the rope. So those are all the forces that act. The problem states I don't have to worry about friction in this case. So the next step then would be to split these forces up into x and y components. So if I start with gravity, I know that gravity, or the weight of the child plus sled, is pointing in the minus y direction. It has no x component. It's just going all in the minus y. The normal force is pointing upward, so it's pointing in the positive y direction. And so then I only have to worry about tension force. And as you can see, tension has a component in the x and a component in the y direction. So I'm going to redraw just that one force along with a coordinate system to make it a bit easier to split up into components. So here is the coordinate system, and then here is my tension force. making an angle of 20 degrees with respect to the horizontal. So then if I drop a line down to the positive x-axis, I can see that this is the x component, this is the y component of the tension force. So then if I take the cosine of the 20-degree angle, the cosine of 20 would be adjacent, which is the x component, over the hypotenuse. So the x component is equal to the tension force times the cosine of 20 degrees. And then if I do the similar thing with the sine of 20 degrees, the sine of 20 is opposite, which is the y component over the hypotenuse. So the y component is going to be equal to the tension times the sine of 20 degrees. So now I can put the x and y components into my chart. So the x component is t cosine of 20. The y component is t sine of 20. And these are both pointed in the positive x and positive y directions. So now I can sum my forces. So if I sum the forces in the x direction, I only have one force in the x direction, and that would be t cosine of 20 degrees, and that's going to be equal to the mass times the acceleration of the sled in the x direction. Similarly, if I sum the forces in the y direction, I get the minus mg plus the normal force plus t sine of 20 degrees, and that's equal to the mass times the acceleration in the y direction. But if I consider the motion of the sled is only going to move forward. It's not going to hop up into the air. So there's actually no motion in the y direction, so there's no acceleration in the y direction. The sum of these forces is equal to 0. So I can look at my motion equations that I have here and think about, well, what am I trying to solve for? I want to know the acceleration of the sled. I want to know the acceleration in the x direction. I know the mass of the child plus the sled, and I also know the tension force of the rope. So it looks like just using this equation, I have enough to solve for the acceleration of the sled. So if I rewrite this, the acceleration of the sled in the x direction is going to be equal to t times the cosine of 20 degrees divided by the mass of the child plus sled combination. So putting numbers into this expression, the tension force we said was 10 newtons times the cosine of 20 degrees divided by the mass of the child plus sled object, which would be 25 kilograms. And if I put that into a calculator, I'm going to get a number that's about 0.38 meters per second squared. So that would be then the acceleration of the sled in the y direction. So finally, let's consider a third problem involving forces and masses and accelerations. This problem involves something called the Atwood's machine. The Atwood's machine is a very simple thing. It's just two masses on a string, and the string is slung over the pulley. Now, of course, whichever mass is heavier is going to win, and will start accelerating downward while the other mass accelerates upward. So we're told that we have these two masses with masses m1 and m2. We don't know what the exact numbers are, but we should still be able to come up with an expression for the acceleration of the two masses that involves the two masses. And then once we get numbers for those two masses, we could just plug them into the equation that we get. So like before, the first step is going to be to draw a picture of this situation. So we have a pulley, and slung over the pulley is a string that's attached to these two masses. And we have one mass, which is labeled M1. We have another mass, which is labeled M2. And it appears that M2 is bigger than M1. It's more massive. So when we have two masses that are attached to each other, they're going to accelerate at the same rate because they're on the same string. If one is accelerating, the other one has to accelerate at the same rate. And so the acceleration of one will be the same as the acceleration of the other. The only difference is one of these masses will be accelerating downward, and then the lighter mass would be accelerating upward. So when you have a situation like this, where you have two connected objects, and you know that their acceleration is going to be the same, a good strategy to use is to choose a direction that corresponds to positive acceleration, and then let that be the positive direction for each one of the objects. So when you're setting up your coordinate system, you choose the direction of acceleration to be the positive direction. So if I do that in this case, I'm expecting M2 to accelerate downward, M1 to accelerate upward, and so I will choose this direction to be the positive direction for acceleration. So that means as M2 accelerates downward, it has positive acceleration, and as M1 accelerates upward, it has positive acceleration. What this implies is that for M2, the downward direction is the plus y direction, and for M1, upward is the plus y direction. That may seem a little bit confusing, but remember, these coordinate systems we can choose. We have total freedom to choose, and by making the two coordinate systems have the direction of positive acceleration be positive, we greatly simplify our problem. So next, let's draw a free body diagram for each one of the two masses. So first I'll focus on mass 1. So here I am drawing a free body diagram for M1. M1 is going to have two forces acting on it. There's going to be a downward gravitational force, and then also an upward tension force from the rope. And so then if I sum the forces in the y direction for mass 1, I'm going to have, well, I have to choose the direction that's positive. So as we said before, upward, this mass is going to be accelerating upward, so upward is my positive y direction. So that means I would have tension force minus m1g is going to be equal to m1 times its acceleration. So that's mass 1. Next, let's focus on mass 2. So mass 2 I will also represent with a dot. And likewise, mass 2 is going to have its mass, its weight, pulling downward. This one should be m1. This one is m2. And then, since it's attached to the same rope, it will have the same tension force in the upward direction. Now remember what I said, m2 is accelerating downward, and I'm making the direction of acceleration for these two linked objects to be the direction of positive motion. So that means I'm going to choose a coordinate system where downward is the positive y direction. If I do that and then sum the forces in the y direction for this second mass, m2g is in what I've defined as the positive y direction, and then the tension force is in the negative y direction as I have defined it here. That's going to be equal to m2 times acceleration. And now, since I've defined the positive direction to be the direction of acceleration, these two accelerations will be exactly the same. So the final step then is to solve for that acceleration. I want to know what is going to be this common acceleration. So since this is the quantity that I want to solve for, I want to get rid of the other things in the equation that I don't want to have to know. And in this case, I'm assuming that eventually someone will tell me what M1 and M2 are. So the thing that I would really rather get rid of in this equation is the tension force. If I have an equation that doesn't have any tension force in it, then that will make me happy, because then I can have an equation for acceleration, and when someone tells me what the masses are, I can just plug in those numbers to my acceleration equation. So what I'll do is I'll first solve this first equation for the tension force. So I'll solve for tension, and then I can plug it into the second equation, and I will only have an equation that involves acceleration and the masses. So if I do that, if I solve this first equation for tension, I can move this first term to the other side, and I will have that tension is equal to M1G plus M1A. Then I can take this expression here and plug it into this second equation for tension, since it's equal to the tension force. So then that would give me M2G minus the tension force, which is M1G plus M1A, is equal to M2A. Okay, so now I have an equation that only has acceleration and the two masses in it, and g, which of course I know. So the next thing I'll want to do is to solve for the acceleration. So to do that, first I think I'll distribute the minus sign over the parentheses. M2g minus M1g minus M1a is equal to M2a. Next, I'll need to get all of the stuff that involves a onto one side of the equation. So I'll add this term to both sides. M2g minus M1g is equal to M1a plus M2a. So then next, since I'm going for acceleration, I'll factor it out of both of these two terms. M1 plus M2 times A is equal to M2g minus M1g. And then finally, I can divide both sides of this equation by M1 plus M2. So my acceleration is going to be M2g minus M1g divided by M1 plus M2. And if I wanted to simplify it even further, I could say M2 minus M1 times g is equal to, or divided by M1 plus M2, and that is equal to my acceleration. Now, if I look at this expression, I should try to figure out if it makes sense, given the physical situation that I have. So imagine that indeed M2 is bigger than M1, so maybe M2 is 10 kilograms and M1 is only 5 kilograms. If M2 is 10 kilograms and M1 is 5, then M2 minus M1 is positive. G is positive, it's 9.8, and then M1 plus M2 is also going to be positive, so the acceleration will be positive, meaning that the object or the system will accelerate in the positive direction. M2 will accelerate downward and M1 will accelerate upward, as I said would happen before. So that makes sense. If M2 is bigger than M1, then I get a positive acceleration, or I get an acceleration in the direction that I have defined to be positive. What if the opposite were true? What if M1 was the bigger mass? Well, if M1 was bigger than M2, then this quantity would be negative, and my acceleration would be negative, meaning that M2 would go upward and M1 would go downward, which is also what I expect to have happen. So finally, think about this question. If the net force acting on an object is in the positive x direction, is it true that the object will move only in the positive x direction?